Wanted to work through an example that involves the direction of the magnetic force on a moving charged particle in a magnetic field. It's a application of the right-hand rule, and specifically, it's an application of the right-hand rule where the velocity vector v of the particle, the magnetic field vector b of the field, are not at right angles to one another. But when they're at right angles to one another, I think that makes the right-hand rule a little bit simpler to apply, a little bit simpler to think of. This is a case where they're not at right angles to one another. So I've got four sketches, one top left, two that's in the top right, and then 3 and 4 in the bottom row here. In each case, I've got a magnetic field that's from left to right. And I'm imagining these are the same magnetic fields. In the four cases, I've got four velocity vectors. I'm imagining they're the same speeds, the same magnitudes, but they're different directions, and they're different directions with respect to the magnetic field. So there's this direction in one where the velocity vector is at some angle above the magnetic field vector. The one below it is some angle below the magnetic field vector. And then there's these two over here on the right where the velocity vectors are also up and down, but they're also in the opposite direction rather than the same direction as the magnetic field. So we're going to just go through and answer the question, what is the force, the magnetic force direction in these four cases? This is an application of the right-hand rule for the case where the velocity vectors and the magnetic field vectors are not perpendicular to one another. But actually, we're not even going to really begin with the right-hand rule and the direction of the velocity of the magnetic field in the sense of the right-hand rule. I'm just going to make one important observation that applies to all four of these orientations of V and B. In all four cases, the vector B is in the plane of the page. The vector V is in the plane of the page. The vectors V and B live in that plane of the page, and the right-hand rule, or the relationship between the magnetic force, magnetic field, and velocity, is that the force is at right angles to both V and B. Therefore, the force has to be at right angles to the plane of the paper. Therefore, that the force has to be either out of the page or into the page. Without worrying about doing this or that for the right-hand rule, I know because V and B are in the plane of the page in all these four sketches that the force on that moving charged particle in that magnetic field is either going to be a force that's straight out of the page or straight into the page. So as I'm using the right-hand rule, I'm just going to be using it to figure out whether that force is into the page or out of the page. So when we apply the right-hand rule, we start with the velocity vector. I'll use the palm of my hand as the direction of the velocity vector. We then curl our fingers towards the magnetic field direction. So I would curl my fingers towards the direction of the magnetic field. And then the thumb of my right hand would point in the direction of the magnetic force on a positively charged particle. So we're going to do that. So rather than do that for each of the four cases, showing you this, where you can't even see where the page is located, I'm going to draw on the sketch how I curl my fingers. And I'm going to draw on the sketch how I curl my fingers for the four different cases. So in case number one, I would be curling my fingers from the direction of the velocity vector around to the magnetic field vector. So I'll be curling my fingers in the direction of this arrow here. In case number three, let's do the case below it. I point the palm of my hand in the direction of the velocity vector in blue here, and I would curl my fingers around towards the magnetic field vector here. So this is the direction in which I curl my fingers. If I was over here on the right-hand side, it might seem that this is a little more complicated and a little bit more ambiguous. But again, I would point the palm of my hand in the direction of the velocity vector v, and I would curl my fingers in the direction towards the magnetic field. Downstairs here, I would point the palm of my hand in the direction of the velocity vector, and I would curl my fingers, as indicated by this arrow, in the direction of the magnetic field vector. I would not try and curl them the other way around. So trying to go this way around, no. Trying to go this way around, no. That's because, if you go those ways around, first you're going away from the velocity, for the magnetic field vector. You're not going towards the magnetic field vector, so that's not the right way to go. So these 4 arrows indicate the 4 directions to head in as you curl your fingers of your right hand towards the magnetic field vector. So if I go ahead and do that with my right hand, I find that for the first sketch, so sketch number 1, if I curl my fingers from the direction of V to B, my thumb is pointing in towards the screen. I'm going to indicate with a cross. That's the direction of the force into the screen on a positively charged moving particle. If I do the same thing on this sketch number 2, again, curling my fingers from the direction of V towards B, my thumb points in towards the page. I'm going to indicate that with a cross, as a convention. That's the direction of the force on a moving, positively charged particle. When I go down to sketch number 3, if I curl my fingers now from V to B, then that's curling them up the page. Then my thumb is pointing out of the page. I'm going to indicate that with a green dot. And that's the direction of the force on a positively charged particle. And likewise for this final diagram here, if I curl my fingers with my palm first pointing in the direction of V, curl them round towards B, then my thumb is pointing out of the page, out of the screen. I'll indicate that with a dot, and that's the direction of the force on a moving charged particle. And so that's how I went ahead and applied the right-hand rule in this particular case. Now, to help us understand this a little bit more, maybe help us understand this a little bit more, I've actually decomposed the velocity vectors, the blue velocity vectors, into 2 components. I've labeled these 2 components V subscript 2 parallel lines, meaning V subscript parallel component, and V subscript perpendicular, meaning the perpendicular component of the velocity. By parallel and perpendicular, I'm meaning the components of the velocity vector that's perpendicular to the magnetic field and parallel to the magnetic field. So, for example, all these V parallels, this line here is parallel to the magnetic field. This magenta line here, parallel, anti-parallel to the magnetic field. And likewise downstairs, the V parallels are parallel to the magnetic fields. The V perpendiculars are the components of the velocity vector that are at right angles to the magnetic field. So there are right angles in all of these angles between V perpendicular and the magnetic field. So that's just to show you that in this case where the velocity vector and the magnetic field vector are not simply perpendicular to one another, you can think of the velocity vector as having a component that is perpendicular and another component that is parallel. So this is interesting because if you look at the perpendicular components of the velocity vectors, the components that are perpendicular to the magnetic field, that's the part that's going to make the magnetic force. If you look at the parallel components that are either along the direction of the magnetic field or opposite the direction of the magnetic field, those actually don't make any magnetic force whatsoever. So if you want to focus on the motion that's creating the magnetic force, then you really want to focus on these perpendicular components of the velocity to the to the field, to the magnetic field. So I'm going to highlight those. If you highlight those, you see why sketch 1 and sketch 2 have the same, exactly the same orientation for V perpendicular and B, and they both create forces that are out of the screen. So from the perspective of the perpendicular motion to the magnetic field, sketches 1 and 2 look the same, and the forces are the same. Likewise, downstairs here, sketches 3 and 4. From the perspective of the perpendicular component of the velocity with respect to the magnetic field, both of these sketches look the same. The components are below the magnetic field lines in the lower two sketches. The components V perpendicular above the magnetic field lines in the upper two sketches. So for the lower case 2, the resulting magnetic force is the same direction. It's out of the screen because the perpendicular component of the velocity was in the same direction in these two sketches. Anyway, that was an example, an illustration of the right-hand rule applied to this little bit more challenging case where the velocity vector and the magnetic field vector are not at right angles to one another. I stress that immediately you know that the force vector must be perpendicular to both these vectors, V and B, and therefore if you've drawn the velocity vector and the magnetic field vector in the plane of the page, the force vector can only be in or out of the page, and the right-hand rule is really only telling us whether it's in or out. When you apply the right-hand rule, even though these vectors are not at right angles to one another, then you still are curling your fingers from the velocity vector towards the magnetic field vector in each of the cases. I indicated that with the black arrows. That is the direction of curl of my fingers. That then told us, through the direction of my thumb, whether the forces were into or out of the page. So we saw here and here that the forces were into the page as we curled my fingers clockwise. And we saw that downstairs here that the forces were out of the page as I curled my fingers counterclockwise. We also saw finally that we could understand this by not thinking about the force vector, but just thinking about the part that's perpendicular to the magnetic field, because that's the only part that causes a magnetic force. The parallel part, or any parallel part of the velocity vector to the magnetic field has no role, no impact in creating a magnetic force.